Okay, in this lecture we're going to cover our section 4.4 material on the method of variation of parameters for higher order non-homogeneous linear equations. So let's start by considering a non-homogeneous nth order linear equation of the following form, where these coefficient functions p1, p2 up through pn and the function g on the right-hand side of our equation are all continuous functions, so that a solution will exist. Now we know for any non-homogeneous linear equation, our first step is to solve the corresponding homogeneous equation. So let us suppose that we have found n solutions, y1, y2, up through yn, and they form a fundamental set of solutions for the corresponding homogeneous equation, so that the general solution of the homogeneous equation, what we call the homogeneous solution, is of the form y sub h is c1y1 plus c2y2 and so on up through cnyn. Now our next step in finding the general solution of a non-homogeneous equation is to find some particular solution of the non-homogeneous equation. And just like we saw for the method of variation of parameters for second order non-homogeneous linear equations, we're going to use the same approach here, where we will replace the constants c1, c2 up through cn in the homogeneous solution by functions of t instead of constants. So that is, we're going to consider a particular solution of the form capital Y is u1 y1 plus u2 y2 and so on up through un yn, where u1, u2, and up through un are now functions. And then we need to try to determine what are the functions u1 through un that would make this a solution of our non-homogeneous equation. Which means that we need to substitute this expression for our particular solution and its derivatives into our non-homogeneous equation, equation number 1. So let's start by calculating our first derivative. By the product rule, our first derivative of this particular solution would be given by u1 prime y1 plus u2 prime y2 up through un prime yn plus u1 times y1 prime plus u2 y2 prime and so on up through un yn prime. And when I think ahead, when I'm going to substitute y and these derivatives into equation 1, I need to solve for these functions u1 through un. So for simplicity, I'm going to make an assumption that the sum of all the terms involving the derivatives of u1 through un is equal to 0. Because when I substitute these expressions into equation 1, I don't want any expressions involving the derivatives of u1 through un. So just like we did for the method of variation of parameters for second order non-homogeneous linear equations, let us add the condition that the sum of these terms involving the derivatives of u1, u2, and so on is 0. So if the sum of all these terms is equal to 0, then our expression for the derivative y prime reduces to u1 times y1 prime plus u2 y2 prime, and so on up through un times yn prime. So if we now calculate a second derivative, y double prime of t, again by the product rule, we would have u1 prime y1 prime plus u2 prime y2 prime, and so on up through un prime yn prime plus u1 y1 double prime plus u2 y2 double prime, and so on up through un yn double prime. And as we did for the first derivative, I'm going to impose the condition that the sum of all these terms involving the derivatives of u1 through un is 0, so that when I substitute into equation 1, I don't have anything involving the derivatives of u1 through un. So here, I'm going to force u1 prime times y1 prime plus u2 prime y2 prime up through un prime yn prime to be 0, which means that my expression for the second derivative, y double prime, reduces to u1 y1 double prime plus u2 y2 double prime, and so on up through un yn double prime. So if we now continue this process and calculate our higher derivatives, y triple prime up through the n minus first derivative, and after each differentiation, we set equal to 0 the sum of these terms involving the derivatives of u1 through un, as we did for our first two derivatives, then we obtain the following set of conditions. So let's take a look here, looking at these conditions we imposed. For our first derivative, we said the sum of these terms u1 prime y1, u2 prime y2, and so on have to be 0. For the second derivative, we said the sum of these terms, u1 prime y1 prime, u2 prime y2 prime, and so on, have to be 0. And so more generally, we have the condition that u1 prime times the nth derivative of y1 plus u2 prime times the nth derivative of y2, and so on, all have to sum to 0 for the m values, the order of the derivative, going from 1 to the n minus second derivative. And after each of these simplifying assumptions, let's see what we're left with. For the first derivative, we had the sum of these products, u1 y1 prime, u2 y2 prime, and so on. For the second derivative, we had the sum of terms u1 y1 double prime, u2 y2 double prime, and so on. So as a result of our simplifying assumptions, it follows that the expression for my first derivative up through the n minus first derivative reduces to the following. So in general, the mth derivative is the sum of these terms, u1 times the nth derivative of y1, u2 times the nth derivative of y2, and so on, for m from the first derivative up through the n minus first derivative. So continuing on, we need to also impose the condition that capital Y is a solution of equation 1, our non-homogeneous equation. So let's get an expression for the nth derivative. By taking the derivative of our n minus first derivative, we find that the nth derivative of this particular solution by the product rule is given by u1 prime times the n minus first derivative of y1 up through un prime times the n minus first derivative of yn plus u1 times the nth derivative of y1 up through un times the nth derivative of yn. And so now taking these expressions that we have found for y and its derivatives and substituting into our non-homogeneous equation, equation 1, and by grouping the terms involving each of the functions, y1 through yn, let's see what we have. So for equation 1, we're looking at the nth derivative of y plus p1 times the n minus first derivative of y up through pn times y, and we need this to equal to the forcing function g of t. So substituting these expressions in, let's see what we have. For the first part of my nth derivative, I have this u1 prime times the n minus first derivative of y1 up through un prime times the n minus first derivative of yn plus grouping all of these other terms according to the functions u1 through un, I would have u1 times the nth derivative of y1 up through pn times the nth, or times y1 itself, and so on. I would have a similar term for grouping all of my u2 terms together, up through un times the nth derivative of yn up through p1 times yn itself. And this still needs to equal my g of t function. But we were saying that y1, y2 up through yn were a fundamental set of solutions for the corresponding homogeneous equation. So each of these terms that we have following these u functions is exactly the differential equation 1 with these y1, y2 up through yn functions substituted in, which means that each of these terms is 0, since this was a solution, or since these functions were solutions of the homogeneous equation. So we are left with u1 prime times the n minus first derivative of y1 plus u2 prime times the n minus first derivative of y2, and so on up through un prime times the n minus first derivative of yn has to equal to g of t. So what we're left with, if we look back at our conditions that we imposed from calculating our derivatives of our particular solution, capital Y, along with this last condition, we obtain a system of linear algebraic equations for the unknown quantities u1 prime, u2 prime, up through un prime. So when we calculated the first derivative, we said the sum of all of these terms had to be 0. For our second derivative, we had the sum of these terms had to be 0. For the third derivative, the sum of these terms all have to be 0, and so on. And then in order for capital Y to be a solution of the non-homogeneous equation, we need the sum of these terms to equal g of t. And in order to solve a system of linear algebraic equations, we could make use of Cramer's rule from linear algebra. And so we would find that the derivative of the function um is given by the following ratio. We would have g of t times w sub m of t divided by w of t, where w of t denotes the Wronskian of the set of solutions for my corresponding homogeneous equation, y1 through yn, and w sub m of t is the determinant obtained from the Wronskian by replacing the mth column by the column vector 0, 0, 0, so on, and 1 for that last entry. So it follows then, once we know what the derivative of is, that would be the antiderivative of that expression. And so using this notation, we find a particular solution of our non-homogeneous equation is given by y sub p of t, or capital Y of t, and it would be the sum of the product of these functions times ym, from m equals 1 to n. That is u1 times y1 plus u2 y2 up through yn. So now that we have derived an expression for this particular solution, using variation of parameters for a higher order non-homogeneous equation, let's look at some examples. In this first example, we are asked to find the general solution of this third order linear non-homogeneous equation. So our first step is to consider the corresponding homogeneous equation. So let's start there. Let us consider the equation y triple prime plus y prime equals 0. And we know to solve this, we could look for solutions of the form y is e to the rt, so that r satisfies the characteristic equation r cubed plus r is 0. So factoring out an r, I'm left with r squared plus 1 is 0. And it follows that r is either 0 or plus minus I. So that means that our homogeneous solution would be of the general form c1 times e to the 0 plus c2 times cosine of 1t plus c3 times sine of 1t. Now, in order to find our particular solution, we see that our g of t function on the right-hand side is tangent t. It doesn't involve polynomial, exponential, or sine cosine, so we can't use undetermined coefficients. So we're going to need to use variation of parameters. And the first thing that we need to calculate to make use of this variation of parameters formula we derived is the Wronskian of this set of solutions. So here let me say the Wronskian of these three functions. Let's say y1 was e to the 0, or 1. y2 is cosine t. And y3, let's call sine t, is given by w of t. And it's the determinant of the 3x3 matrix we get, where we have, for our first row, our functions. For the second row, we would have our derivatives, 0, negative sine t, cosine t. For our last row, 0, negative cosine t, negative sine t. So here, using a cofactor expansion down the first column, I would have 1 times sine squared t minus a negative cosine squared t, so plus cosine squared t, which leaves me with 1. And now the next thing I need to calculate are these other determinants, what we call Wm of t, for m equals 1 through 3. So first, for w sub 1, I'm going to take the determinant that we had for the Wronskian, but replace my first column by the vector 0, 0, 1. And then my second two columns remain the same. And so using a cofactor expansion down the first column again, I'm left with 1 times cosine squared t minus a negative, so plus sine squared t, which is again 1. Next up, for W2, I take the Wronskian and I replace the second column by the vector 0, 0, 1. So my first column and my third column are the same as what we had for the Wronskian. And so again, using a cofactor expansion down the first column, I have 1 times 0 minus cosine t. And then finally, for W3, I take the determinant of the 3x3 I get by taking the third column of my Wronskian and replacing it by the vector 0, 0, 1. So my first two columns are going to be the same as what we had for the Wronskian. And so again, using a cofactor expansion down the first column, I have 1 times negative sine t. So once we have calculated these expressions, we're ready to find our u1, u2, and u3 functions. Let's take a look. To get u1, we take the integral of g of t, which was tangent t, times w1, which was just 1, divided by the Wronskian, which was just 1, integrating with respect to t. So we have just the antiderivative of tangent, which by using a u substitution is the negative natural log of cosine t, or if you prefer, the natural log of secant t. Then for u2, we're calculating the integral of g of t, which was tangent t, times w2, which was a negative cosine t, divided by the Wronskian, which was just 1 dt. And since tangent is just sine divided by cosine, this product leaves us with negative sine t dt. And so my antiderivative is then a positive cosine t. And then lastly, for u3, we take the integral of g of t, which was tangent, times w3, which is a negative sine t, divided by the Wronskian, which was just 1 dt. And again, since tangent is sine divided by cosine, this product leaves me with negative sine squared t divided by cosine t dt. And since sine squared of t would just be 1 minus cosine squared, my numerator, negative sine t, is cosine squared t minus 1. I'm still dividing by cosine t. And so if I split up this integral, I have cosine t minus 1 over cosine, which is secant t dt. And evaluating my antiderivative term by term, I have sine t minus the antiderivative of secant is the natural log of secant plus tangent. So we have the following. So now let's write out our particular solution. Capital Y is defined as the product of u1 times y1. So we have u1, which is negative log of cosine t, times y1, which was just 1, plus u2 times y2. Now u2 was cosine of t, y2 was also cosine t, so we have cosine squared t, plus u3 times y3. Now y3 was sine of t, so multiplying the expression that we found for u3 by sine, we get sine squared t minus sine t times the natural log of secant t plus tangent t. And then for this part of our particular solution, we see that we have the sum of sine and cosine squared, which reduces to 1. So we have the negative natural log of cosine t plus 1 minus sine t times the natural log of secant t plus tangent t. And so for our general solution of this non-homogeneous equation, we take the sum of our homogeneous solution, which was c1 plus c2 cosine t plus c3 sine t, and we add our particular solution, which was negative log of cosine t plus 1 minus sine of t times the natural log of secant t plus tangent t. And we can simplify a little bit here. It's not necessary, but it helps to simplify the form of our solution. So when I have this general solution for y, I have this term c1, which is an arbitrary constant. And then from my particular solution, I'm adding a factor of 1. So if I group those two terms together, I have c1 plus 1. But since c1 was an arbitrary constant, c1 plus 1 is also an arbitrary constant. So I could group those two terms together as a single constant. Let's just call it c1 plus c2 cosine t plus c3 sine t minus the natural log of cosine t minus sine t times the natural log of secant t plus tangent t. And this would be my general solution of that third order non-homogeneous equation. So we see here, as we would expect for higher order equations, the method of variation of parameters becomes a bit more complicated since we have more antiderivatives to evaluate. So let's look at another one. In this next one, we are asked to find a general solution to the Cauchy-Euler equation shown here, where x is positive, given that x squared, and x cubed is a fundamental set of solutions of the corresponding homogeneous equation. So here we're told that this set of functions, x squared, x cubed, is a fundamental set of solutions for the homogeneous equation, which means that for this equation, our homogeneous solution, y sub h of x here, since we have functions of x, is a c1 times x to the first power plus c2 x squared plus c3 x cubed. And to use the method of variation of parameters, I need to make use of, I need to find the Wronskian of this fundamental set of solutions. And let's justify before we move forward why we need to use a variation of parameters here. When I take this equation that I'm given, and I rewrite it in standard form, I would divide everything through by x cubed, the coefficient in front of my highest derivative, y triple prime, and I get y triple prime minus 3 over x, y double prime, plus 6 over x squared, y prime, minus 6 over x cubed, y. That's equal to x to the negative 1, or 1 over x, divided by x cubed. So that gives me 1 over x to the fourth, or x to the negative 4. So here, the right-hand side, this g of x function, is not a polynomial, exponential, nor sine-cosine function. So the method of undetermined coefficients is out, and I need to rely on variation of parameters. So again, to make use of this variation of parameters approach, I need to find the Wronskian of this fundamental set of solutions, y1 which was x, y2, which was x squared, and y3, which was x cubed. So here we're going to have the Wronskian, which will be a function of x, and it's given by the determinant of the 3 by 3 matrix we get by taking our first row to be the solutions, x squared, x cubed. Our second row would be the derivatives, 1, 2x, 3x squared. And our third row would be the second derivatives. So looking at a cofactor expansion down the first column, we would have x times 12x squared minus 6x squared, and then minus 1 times 6x cubed minus 2x cubed. So this gives me, let's see, x times 6x squared would be 6x cubed minus a 4x cubed. So 2x cubed for that Wronskian. And then I need to calculate these other determinants, W1, W2, and W3. So let's start with W1, which is the determinant of the 3 by 3 matrix I get by replacing the first column of my Wronskian by the vector 0, 0, 1. And then my second two columns remain the same. So using a cofactor expansion down the first column, I have 1 times 3x to the fourth minus 2x to the fourth, or just x to the fourth. W2 is the determinant I get by taking the Wronskian and replacing the second column by 0, 0, 1. So my first and third columns will remain the same. And using a cofactor expansion down the second column, I get a negative 1 times 3x cubed minus 1x cubed. So a negative 2x cubed. And lastly, for W3, I take the determinant of the 3 by 3 matrix I get by replacing the third column of the Wronskian by 0, 0, 1. So my first two columns remain the same. And using a cofactor expansion down the third column, I have 1 times 2x squared minus 1x squared, which leaves me with x squared. So now let's take a look at calculating our u functions. For the first one, u1, which will be a function of x, we take the integral of our g of x function, which was the function on the right-hand side of our equation after it's written in standard form. So looking back up here, this g of x function will be 1 over x to the fourth, or x to the negative fourth. So we have x to the negative fourth times w1, which was x to the fourth, divided by the Wronskian, which was a 2x cubed dx. And so this simplifies to half the integral of 1 over x cubed, or x to the negative third dx. And so we're left with 1/2 divided by negative 2, which would be negative 1/4 x to the negative 2. Then for our second u function, u2, we have the integral of our g of x function, which was x to the negative 4th, times w2, which was negative 2x cubed, divided by the Wronskian, which was 2x cubed dx. And so this leaves us with a negative 1 x to the negative 4th dx. And so we get a positive 1/3 x to the negative third. And then finally, for u3, we have the integral of g of x, which was x to the negative 4th, times w3 x squared, over the Wronskian, 2x cubed dx. And this leaves us with 1/2 the integral of x to the negative 2nd divided by x cubed, so x to the negative 5th dx. And so our antiderivative, we have 1/2 divided by negative 4, be negative 1/8 x to the negative 4. And so now our particular solution of this non-homogeneous equation, capital Y of x, is given by u1 times y1. So y1 was x to the first multiplying by u1, gives us negative 1/4 x to the negative first, plus u2 times y2. Now y2 was x squared multiplying by u2, gives us 1/3 x to the negative first, and then plus u3 times y3. y3 was x cubed multiplying by u3, gives us 1/8 x to the negative 1. Or combining these terms, we're left with a negative 1 over 24 x to the negative first power. And therefore, our general solution of this non-homogeneous equation is the sum of our homogeneous solution, c1 x to the first, plus c2 x squared, plus c3 x cubed, plus our particular solution, negative 1 over 24 x to the negative first. Okay.